Welcome back to another deep dive, everyone. Today we're going to be tackling something I think a lot of you have probably heard of, but probably haven't really dug into the real nitty-gritty details of. That's Bayesian inference. It's a huge field. There's just so much out there. It's really hard to kind of even know where to begin.
Yeah, there's a ton of resources out there, but the real challenge is like, how do you go from just kind of understanding the basics to really grappling with some of the more advanced ideas and the cutting edge, the state-of-the-art stuff. So that's what we're going to try to do today, specifically by digging into a particular paper. The title is A Geometric Ensemble Method for Bayesian Inference.
A geometric approach. Huh. That's interesting. Usually when we're talking about Bayesian inference, we're thinking about like, probabilities and distributions and all these, kind of abstract statistical things. And here they're bringing in geometry. What's the big idea here? Why geometry?
Yeah, so traditionally when people think about Bayesian inference, they're usually thinking about, like you said, probability distributions, which are often like visualized as these kind of like, bell curves or maybe just clouds of points. But this paper takes a completely different approach. Instead of thinking about distributions as like these continuous smooth things, they're representing them using geometric shapes called convex polytopes.
Convex polytopes. Okay. So like I guess like a cube would be a simple example of a polytope.
Yeah, exactly. A cube is a simple example, but polytopes can exist in any number of dimensions, not just three. So you could have like, 4-dimensional polytopes, 5-dimensional polytopes, even higher.
Right. And why are these polytopes particularly well suited for Bayesian inference? Like what advantages do they offer?
Well, one of the big advantages is that they allow you to represent uncertainty in a much more kind of well-defined way, compared to using something like, a Gaussian distribution or a set of point particles. So, with a Gaussian distribution, the tails extend out to infinity. But with a polytope, you have these hard boundaries. So you can say, okay, with certainty, the true value lies within this region, within these boundaries.
So it's like a more, I guess, a more precise way of defining where our uncertainty lies. Like we're saying we absolutely know that the true value must be somewhere within this particular shape.
Exactly. It gives you a much more kind of clear and definite representation of the possible range of values that the quantity of interest could take.
Yeah. And they also mentioned that there's a couple of ways to describe these polytopes. You can define them by their corners, or you can define them by the flat surfaces that enclose them. But they seem to prefer this the hyperplane representation that they call them H polytopes. Why that choice?
Yeah, that's a good question. And the reason for that is because it turns out that when you're dealing with Bayesian inference, a lot of the operations that you need to perform become computationally much more efficient when you're using the hyperplane representation.
Okay. Well, let's get into some of the specifics of this H polytope representation. They give us a formal definition for an H polyhedron. It's written as PHAB equals XOAB. XO's run.
Yeah.
Can you unpack that for us?
Yeah, absolutely. So this definition might look a little bit intimidating at first, but it's actually not too complicated. So let's break it down piece by piece. So first we have this symbol, PHAB. This represents the H polyhedron itself, and it's defined by two things, A and B. A is a matrix. It's a grid of numbers. And B is a vector, which is basically just a list of numbers.
Okay, and what do these numbers represent? Like what's the A matrix? What role does that play in defining the shape of the polyhedron?
Yeah, good question. So each row of the A matrix defines a hyperplane. And a hyperplane, you can think of it as like a flat surface in n-dimensional space. So, in 2 dimensions, a hyperplane is just a line. In 3 dimensions, it's a plane. And then in higher dimensions, it's just this flat surface. And the numbers in each row of A, they give you the orientation of that hyperplane.
Oh, okay. So the A matrix is basically telling us like the direction that each of these flat surfaces is facing.
Exactly. And then the B vector, that tells us where each hyperplane is positioned in space.
Okay, so the A tells us the orientation, the B tells us the position, and then we have this inequality, ax AB. So what is that? What role does that play?
Right, so that inequality, that's what actually defines the polyhedron. So you have all these hyperplanes defined by A and B, and then the inequality XAB, it basically says, okay, the polyhedron is the set of all points that are on the correct side of all of these hyperplanes.
Oh, okay. So it's like, each hyperplane is like a wall or a boundary, and the polyhedron is the region that's enclosed by all of those walls.
Exactly. It's the region of space that satisfies all of the constraints defined by the hyperplanes.
Okay, got it. And then they talk about the difference between an H polyhedron and an H polytope. So what's the distinction there?
Yeah, so an H polytope is a special kind of H polyhedron. It's bounded.
Bounded. What does that mean?
It means that it has a finite size, so you could draw a box around it, and the whole polytope would fit inside that box.
Okay, so it's not like extending out to infinity in any direction.
Exactly. And that's an important property for a lot of the applications that we're interested in, like probability and statistics, because you want your distributions to be normalized, so they have a total probability of 1.
Right, right. Makes sense. And they also mentioned that these bounding hyperplanes that we were talking about, they're not unique. What does that mean?
Yeah, so what that means is that you could have multiple sets of hyperplanes that define the same polytope. Like you could have some extra hyperplanes that are redundant that don't actually change the shape of the polytope at all.
Oh, okay. So it's like having extra rules that don't actually change the outcome.
Yeah, exactly. And that can happen sometimes when you're like combining information from different sources, for example.
Okay, makes sense. And then they introduce some shorthand notation for this. They use Theo for an H polyhedron and Pia for an H polytope.
Yeah.
So I guess that's just to simplify things when they don't need to specifically refer to the A and B matrices every time.
Yeah, exactly. It's just a way to write things more concisely.
Okay. And then they go on to discuss some of the key properties of these H polytopes. The first one being that the intersection of two H polytopes is also an H polytope.
Yeah.
So like if you have two of these shapes and you overlap them, the region where they overlap is also going to be an H polytope.
Exactly. And that's a really important property for Bayesian inference because, you're often combining information from different sources. So, you might have your prior belief represented by one polytope, and then you get a new measurement represented by another polytope, and then the intersection of those two polytopes, that represents your updated belief after you've incorporated the new information.
Okay, so it's like you're taking the region where both sets of constraints are satisfied.
Exactly.
Okay, and then they have a similar property for the intersection of an H polytope and an H polyhedron. They say that the result is also an H polytope as long as the intersection is bounded.
Yeah. So that one's a little bit trickier because an H polyhedron, remember, can be unbounded. So you could imagine a situation where you have a polytope and then you intersect it with a polyhedron that extends out to infinity in some direction. And in that case, the intersection might not be bounded, so it wouldn't be a polytope.
Right. Okay. So it has to be a situation where the polyhedron is actually constraining the polytope in all directions.
Yeah, exactly.
Okay. And then they discuss the effect of applying an invertible affine transformation to an H polytope. So an affine transformation, that's basically just a linear transformation, like a rotation or a scaling, followed by a translation. And they say that if you apply an invertible affine transformation to a polytope, you get another polytope.
Exactly. And that makes sense intuitively because, if you think about what a linear transformation does, it's just, stretching or rotating or reflecting the shape. It's not going to fundamentally change the fact that it's a bounded region with flat sides.
Right. Okay. And then they introduce this concept of a Minkowski sum of two H polytopes. What is that exactly?
Yeah, so the Minkowski sum, it's basically a way of combining two shapes. You can think of it as like taking one shape and sliding it along the boundary of the other shape. And then the Minkowski sum is the set of all points that are covered by that sliding shape.
Okay. And they say that the Minkowski sum of two polytopes is also a polytope.
Yep.
But they also point out that it can be computationally quite expensive to actually calculate this Minkowski sum, especially in higher dimensions.
Yeah, that's right, because the number of faces in the Minkowski sum can be much larger than the number of faces in the original polytopes. So the complexity of the shape can grow very quickly.
Okay. Well, let's move on then to the next section. They talk about defining a uniform probability density function on a polytope. So this seems pretty straightforward. It's basically just saying that every point inside the polytope is equally likely.
Yeah, exactly. It's just a uniform distribution over the volume of the polytope.
Okay. And then they introduce this concept of a Chebyshev center of an H polytope. So what is that exactly?
Yeah, so the Chebyshev center, it's the center of the largest sphere that you can fit inside the polytope.
Oh, okay. So it's like the most central point within the polytope in a sense.
Yeah. Yeah, exactly. It's the point that's furthest away from all of the boundary.
Okay, got it. And they even provide a linear programming problem that we can use to actually find this Chebyshev center.
Yeah, that's right. Because, finding the Chebyshev center, it's basically an optimization problem. You're trying to find the point that maximizes the distance to the closest boundary.
Okay, makes sense. And then they talk about the n-dimensional unit cube. So this is, I guess, just like a very basic H polytope that we can use as a building block.
Yeah, exactly. It's just a cube with sides of length 1 centered at the origin.
Okay. And then they explain how we can take this unit cube and modify it to have a desired mean and covariance.
Yeah.
And they call this new shape Q. So what's going on there?
Yeah, so what they're doing is they're basically taking the unit cube and they're stretching it and rotating it in a way that gives it the desired mean and covariance. And they do that using a matrix square root.
Okay, so the matrix square root is basically just a way of like transforming the shape of the cube.
Yeah, exactly. It's a way of stretching and rotating it.
Okay, and then they make a note about the storage cost of this Q hand shape. They say that it can be ON if we can find a sparse square root decomposition of the covariance matrix. So what does that mean?
Yeah, so the storage cost, that basically just refers to how much memory you need to store the representation of the polytope. And they're saying that, if you have a sparse representation of the covariance matrix, meaning that it has a lot of zeros in it, then the storage cost will be linear in the number of dimensions.
Okay, so it's basically just saying that, if the covariance matrix has a certain structure, then we can store the polytope more efficiently.
Exactly.
Okay. And then finally, they remind us how a point and a normal vector can define a hyperplane. I guess this is just a little bit of basic geometry review.
Yeah, exactly. It's just, showing that there's multiple ways to represent a hyperplane. You can either represent it using the A and B that we talked about earlier, or you can represent it using a point that lies on the hyperplane and a vector that's perpendicular to the hyperplane.
Okay. Makes sense. Well, let's move on then to the next section. This is where they start to actually talk about Bayesian inference itself. So they begin by mentioning prior information and external information. What are they referring to here?
Yeah, so in Bayesian inference, you always start with some prior information about the quantity that you're trying to estimate. And this prior information, it can come from, previous experiments, or it can come from, expert knowledge, or it can just come from your own intuition about the problem.
Okay. So it's basically just like everything that we know about the problem before we start to actually collect any new data.
Yeah, exactly. And this prior information is represented by a probability distribution.
Okay. And then they talk about new information coming in the form of a measurement. So I guess this is like our data that we're collecting.
Yeah, exactly. So, you have your prior belief about the quantity of interest, and then you get some new data. And the goal of Bayesian inference is to update your belief based on that new data.
Okay. And they present the core formula for Bayesian inference, which is Bayes' theorem. It's a bit of a mouthful, but I think it's worth taking a moment to actually understand what it's saying. So can you walk us through that?
Yeah, absolutely. So Bayes' theorem, it basically tells you how to update your belief about a hypothesis given some new evidence. So, in this case, our hypothesis is our prior belief about the quantity of interest, and then our evidence is the new measurement that we get. And Bayes' theorem, it gives you a formula for calculating the posterior probability of the hypothesis given the evidence.
Okay. Yeah. So it's like, we're taking what we knew before, and we're combining that with the new data that we're getting to arrive at a new updated belief.
Exactly.
Okay. Got it. And they make it clear that the goal of all the methods that they're going to discuss is to approximate this Bayesian inference. So why do we need to approximate it?
Yeah. So the reason why we need to approximate it is because in a lot of cases, the the exact calculation of the posterior probability is computationally intractable, meaning that it would take way too much time and computing power to actually calculate it exactly. So we need to come up with some approximate methods that are more efficient.
Okay, so it's basically like a trade-off between accuracy and computational cost.
Yeah, exactly.
Okay. Well, let's move on then to the first specific method that they introduced. This is the convex polytope filter, or CPF. What's the basic idea behind this CPF?
Yeah, so the basic idea behind the CPF is to represent probability distributions using uniform distributions over convex polytopes. And then they use this representation to do Bayesian filtering.
Okay, so what is Bayesian filtering exactly?
Yeah, so Bayesian filtering, it's basically a way of estimating the state of a system over time. So, you might have a system that's evolving according to some dynamics, and then you're getting measurements of the system at different points in time. And the goal of Bayesian filtering is to estimate the state of the system at each point in time, given the measurements that you've gotten up to that point.
Okay. So it's like, you're trying to track the evolution of the system over time based on the data that you're collecting.
Exactly.
Okay, and how does the CPF do this?
Yeah, so the CPF, it does this by representing the uncertainty about the state of the system using a uniform distribution over a convex polytope. And then when you get a new measurement, you update that polytope based on the information in the measurement.
Okay. So it's kind of like we're starting with a polytope that represents our prior belief about the state of the system, and then we're using the measurement to kind of refine that polytope to narrow down the possibility.
Exactly. And they do that by intercepting the prior polytope with another polytope that's derived from the measurement.
Okay, so the interception of two polytopes is another polytope. That's one of the properties that we talked about earlier.
Right.
Okay, and then they go on to discuss a variation on the CPF called the extended convex polytope filter, or ECPF. So what is this ECPF, and how is it different from the regular CPF?
Yeah, so the ECPF is basically an extension of the CPF that can handle nonlinear measurements. So, in the CPF, we were assuming that the measurement was a linear function of the state. But in a lot of real-world applications, that's not the case. So the ECPF, it uses a linear approximation to the nonlinear measurement so that it can still use the same basic framework as the CPF.
Okay, so it's basically just a way of dealing with the nonlinearity in the measurement equation.
Exactly.
Okay. And then they talk about the Kalmanized convex polytope filter, or KCPF. So what is that?
Yeah, so the KCPF, it's basically a way of combining the CPF with the Kalman filter. So the Kalman filter, it's a very popular algorithm for doing Bayesian filtering. And the KCPF, it basically just takes the basic idea of the CPF and incorporates some of the principles of the Kalman filter.
Okay, so it's like a hybrid approach that combines the two methods. Okay, and then they present some numerical examples to kind of illustrate how these different filters work.
Yeah.
And then they move on to talk about ensemble polytope filters. So what are ensemble filters?
Yeah, so ensemble filters, they're basically a way of representing a probability distribution using a set of samples. So instead of trying to represent the distribution analytically, you just represent it using a bunch of points that are drawn from the distribution.
Okay, so it's kind of like a Monte Carlo approach.
Yeah, exactly.
Okay, and how do these ensemble polytope filters work?
Yeah, so in an ensemble polytope filter, each sample in the ensemble is represented by a convex polytope.
Okay, so instead of having a set of points, we have a set of polytopes.
Right.
Okay, and they present three different types of ensemble polytope filters: the bootstrap convex polytope filter, the ensemble convex polytope filter, and the ensemble Kalmanized convex polytope filter. Can you give us a brief overview of each of those?
Yeah, absolutely. So the bootstrap convex polytope filter, it's basically just an extension of the bootstrap particle filter, where each particle is represented by a polytope instead of a point. And then the ensemble convex polytope filter, It's a bit more complicated. It uses a mixture of polytopes to represent the probability distribution, and then the Ensemble Kalmanized convex polytope filter, that's kind of a hybrid approach that combines the Ensemble convex polytope filter with the Kalman filter.
Okay, okay, and they present some numerical examples to show how these different filters perform.
Yeah.
And then they wrap up with some conclusions and future directions. So what are some of the key takeaways from this paper?
Yeah, so I think one of the key takeaways is that this geometric approach to Bayesian inference, it's a really promising new direction. It has the potential to address some of the limitations of traditional methods, and they've shown that it can perform well in both low dimensional and high dimensional settings.
Okay, that's great. Well, that was a really fascinating deep dive. I learned a lot. Thanks so much for sharing your expertise with us.
Yeah, no problem. Thanks for having me.
So for you, the learner, I hope you found this as interesting as I did. It's always exciting to see new approaches to old problems. And this geometric approach to Bayesian inference, it definitely seems to have a lot of potential. I'm really curious to see where this research goes in the future. One thing that I was thinking about as we were talking is how this method could be applied to problems in machine learning. Bayesian inference is used all the time in machine learning, and I wonder if this geometric approach could lead to some new and improved machine learning algorithms. That's something that I'm going to have to look into further. But anyway, I think that's all the time we have for today. Thanks again for joining us, and we'll see you next time.
Welcome back to the deep dive. It can be so hard these days to stay informed, with the constant influx of information, especially when it comes to fields like Bayesian inference. You've probably heard of it before, this whole world of probabilities and beliefs that change when you see something new. You might even know the basics, but like diving into the really advanced stuff, I don't know, it can be pretty daunting, honestly.
And that's precisely what we're tackling today. Think of this as a curated journey, kind of like a deep dive for you into a really captivating area of research. We're going to be exploring this paper called A Geometric Ensemble Method for Bayesian Inference, which introduces a whole new way of looking at this process using shapes, like actual geometric shapes.
Yeah, it's pretty cool. We're going beyond just averages and spreads, or even those clouds of data points you sometimes see. We're stepping into the realm of these things called convex polytopes. They're like building blocks in multiple dimensions with flat sides. And get this, they're really insightful for understanding and approximating Bayesian inference, which is pretty amazing when you think about it. And why should you care about this, you might ask? Well, this geometric approach, it has the potential to go beyond the limits of traditional statistical methods. Instead of just having single kind of fuzzy estimates, we're talking about clearly defined zones of possibility.
And that change in perspective is really important for you. This paper digs deep into how representing uncertainty with these geometric shapes can paint a much clearer picture. It suggests that we might be able to make more reliable and potentially even more accurate inferences, especially when we're dealing with those messy real-world systems that just don't behave in a perfectly linear way.
Right, because the real world is never that clean, right? Now, the paper talks about two ways to describe these convex polytopes. We can define them by their corners, which are called vertices, or by their flat surfaces, which are the hyperplanes. But interestingly, the researchers decided to stick with just the hyperplane representation. They call those H polytopes. Why is that a good choice?
Oh, that's a great question, and it boils down to, well, practicality for you. The authors explain that when it comes to incorporating new information, like adding those extra constraints that narrow down the possibilities, this hyperplane representation, H polytopes, offers some real computational advantages. It's kind of like defining a space by adding walls, right? Imagine you want to make that space smaller. Adding another wall is much easier than redefining everything based on all the corners. Does that make sense?
Totally, I get it. It's like adding a new rule without having to redraw the whole blueprint, so to speak.
Okay, let's dive into these H polytopes, the formal stuff. The paper defines an H polyhedron like this. They write it as PH, AB, E, EA, AB, X, U, I, N. Can we break that down? I think it'll help to actually picture what's going on here.
Of course. This equation, this is the precise mathematical way to define an H polyhedron. We can go through it step by step for you. The N there represents the number of variables or dimensions we're dealing with. So if we're looking at, say, temperature and pressure of something, N would be 2. X is a vector, You can think of it as a list of n numbers. It represents a particular state or combination of those variables. Now, A is a matrix, basically a grid of numbers. It has p rows and n columns. And each row of A, what it does is define the orientation of one of those flat surfaces, those hyperplanes, that are the boundaries of our region. B is a column vector with p numbers. Each number in B tells us how far its corresponding hyperplane is from the origin. It's offset in that n-dimensional space. Okay, so when we see that ax AB, that inequality is saying that for a point X to be inside our H polyhedron, it has to meet a whole bunch of conditions, one for each row of A and the matching part of B. It's kind of like where all those conditions overlap, right? Like intersecting a bunch of half spaces.
Precisely. Each one of those inequalities, like if you take the ith row of A and multiply it by X, and that's less than or equal to the ith element in B, it's written as A sub I, po I, B sub A. What that does is define a half space. It's on one side of that hyperplane. The H polyhedron, written as P sub HAB, it's the set of all those points, all those X's, that lie within or right on the edge of all those half spaces all at the same time. It's like the common area where all the allowed spots overlap. So for you, what this means is we're using linear inequalities to describe shapes that could actually be pretty complex.
Interesting. So we've got these half spaces defining boundaries, and where they all come together, that's our shape. Makes sense. Now, the paper makes a distinction between an H polyhedron and an H polytope. They define an H polytope as PAB equals as XA key solid. Sounds similar, right? But here's the key. They add that it's a bounded H polyhedron. What's that all about? What does bounded mean here, and why should we care?
That's a really important point, that distinction. You see, an H polyhedron, like we just talked about, it can go on forever in some directions. Imagine like a wedge shape going on, or a slab between two parallel planes, infinite in the other directions. But an H polytope, it's fully contained, it's enclosed, it has a limit, a finite extent in all directions. Think of it like this. You could draw a big enough box, and the entire polytope would be inside. A cube, a pyramid, those are finite. They have a defined size. And this boundedness, it's usually a good thing to have when we're working with probabilities, because usually you want the total probability to be a finite number, like 1. A bounded region helps a lot with that. So to put it simply for you, a polytope represents a limited set of possibilities. It's contained.
Okay, so it's like the difference between, say, a fenced-in yard and the whole wide-open world, right?
Yeah.
One's got boundaries, the other doesn't. Gotcha. The paper also mentions that these hyperplanes, those walls we've been talking about, they're not unique. It says there's a minimum number you need to define a polytope, but you can have extra ones. That's kind of strange, isn't it? Why would you have more hyperplanes than you absolutely need?
Yeah, that can seem a bit counterintuitive, right? Let's think about a simple example, something you can easily visualize: a square. To define a square, you need 4 lines, right? That's it. But you could add another line, a 5th one, that's completely outside the square. It's not cutting into it or anything. This extra line, it's still a linear inequality. It could be part of that ax-AB system, but it's not doing anything to change the square itself. These extra rules, they're called redundant or inactive constraints. So basically, while there's a small set of hyperplanes that perfectly define the polytope, those are its actual faces, you can always add more without changing the region itself. It's like having extra rules that don't actually change the game, This happens sometimes, especially when you're combining information from different sources.
I see. It's like those terms and conditions nobody reads because they don't really affect anything, right? Okay. Then they introduce shorthand notation, Schaeffer's for H polyhedra, and P for H polytopes. It seems they're just trying to be concise, like a shortcut.
Exactly. It's just a simpler way to write things, a convenience for now. When they're talking about a general H polyhedron or H polytope, without specifying the A and B every time they can use the shorthand, much easier than writing it all out over and over again.
Right, like a math abbreviation. Makes sense. Okay, so now they get into some important properties of H polytopes. The first one is that if you take 2 H polytopes, let's call them P1 and P2, and you intersect them, the result is also an H polytope. They even show how to find the hyperplanes that make this new, smaller shape. But how is this useful for Bayesian inference?
This property, this is super important in Bayesian inference. Think about how we update what we believe, right? We start with some initial idea, our prior, then we get new info, a measurement. This new info, it's like a restriction, a constraint on what we initially thought. If we think of our prior as one H polytope, that's P1, and the possibilities allowed by the measurement is another one, P2, then where they overlap, that intersection, that's where both sets of conditions are true. It naturally represents our updated belief, the posterior. And the formula they give us is really neat. If P1 is defined by A1x, AB1, and P2 by A2x, AB2, then their intersection is all the x's that satisfy both. You just stack the matrices and vectors together. It looks like this A1, A2x, AB1, B2. And since both P1 and P2 are bounded, this new set is bounded too, so it's an H polytope as well. What this means for you is when you combine different bits of information in this geometric way, you get a new region of possibilities that's well defined. It's pretty elegant, actually.
I like how everything seems to fit together so nicely. So it's like taking two puzzle pieces and seeing where they lock in, right? The overlapping area becomes your new updated understanding. Okay, next up. They say that if you take an H polytope, P1, and intersect it with more general H polyhedron, VH2, the result is still an H polytope, as long as that intersection is bounded. They show how to combine the hyperplanes here, too. Why does it matter that the result stays in H polytope, though?
That's a great question, and it's particularly relevant when we think about sequential Bayesian filtering, updating our beliefs over time. Imagine you have a belief at a certain moment that's perfectly described by a bounded H polytope, that's our P1. Then you get a new measurement. The info from this measurement, it might define an H polyhedron, VH2. This one could be unbounded in some directions if the measurement isn't so informative about some variables. Now, for our updated belief, the one after the measurement still be a nice finite region, something easy to work with in the next step. It's got to stay in H polytope, assuming it's bounded, of course. If it becomes unbounded, it gets a lot harder to represent and use as a prior for the next update.
Got it. It's like if you keep adding more and more to your puzzle, you want it to still fit on the table, right? You need those boundaries. The next property deals with what happens when you apply something called invertible affine transformation to an H polytope. We take P1, multiply every point by an invertible matrix C, and then add a constant vector D, so it looks like CP1 plus D, we end up with another H polytope. They give the rule for how the A and B of this new polytope are related to the original A1 and B1, and that transformation, the C and D. What's the intuition behind this for us non-mathematicians?
Okay, think of this invertible affine transformation like this. You take your shape, your polytope, and you stretch it, you rotate it, maybe you even squish it a little. The key is you don't completely flatten it into a lower dimension. Then you just move it somewhere else. These operations, they don't change the basic geometric features of the polytope. It stays bounded, and those flat sides, the hyperplanes, they stay flat. The transformation rule for A and B, which ends up being A1C for the new A and B1 plus A1CD for the new B, it shows exactly how the orientation and position of those bounding hyperplanes change during this transformation. And the key word here is invertible. If it wasn't invertible, it could crush the polytope down into a lower dimensional space, potentially making it unbounded. That's why you'd end up with an H polyhedron instead. So for you, this means you can linearly transform your representation of uncertainty, and it still behaves nicely as a polytope.
Okay, so it's like taking a clay model, molding it, moving around, but it's still a solid shape, right? I'm with you. Now let's talk about this Minkowski sum. They write it as P1, eero, P2. It's all the possible sums you get when you take a point from P1 and add it to a point from P2. The paper says this sum of two H polytopes is also an H polytope, but finding those hyperplanes for this new shape, it becomes really hard, especially as you go to higher dimensions. Why does this operation become so tough for us in those higher dimensions?
The Minkowski sum, it's kind of like expanding one shape by the size of the other. You're adding the extents together. Even if the original polytopes have just a few faces, those hyperplanes, the Minkowski sum can have a whole bunch of new ones, and in all sorts of weird orientations. Picture it like this. You take two squares and you do this sum. You end up with an octagon. Now imagine doing that in many more dimensions, describing all the new facets, the flat surfaces that come from all those sums, all those combinations of points computationally. It becomes a nightmare. It's like trying to describe an incredibly intricate shape by listing all its flat surfaces. It's just too much. So yeah, even though the concept is useful, actually calculating this in high dimensions is a real roadblock.
It sounds like one of those things that's easy in theory, but a nightmare in practice. Okay, moving on. The paper defines this uniform probability density function on a polytope, P, written as UXP. This seems pretty basic. The constant value, 1 divided by the volume of the polytope for any point inside and 0 outside.
That's right. For you, it basically represents a state of complete neutrality, complete lack of preference within the polytope. Every point inside that region of possibilities is equally likely. And dividing by the volume, well, that ensures that the total probability adds up to 1 when you integrate over the whole polytope. That's a fundamental rule for any probability density function.
Right, it's got to add up to 1. Makes sense. Now, they introduced this concept of the Chebyshev center of an H polytope. They say it's the center of the largest possible sphere you could fit completely inside that polytope. They even give us a linear programming problem to find the coordinates of that center. They call it XC, and the radius of the sphere, AKO-AC. What's so important about finding the center? Why do we care about it in Bayesian inference?
The Chebyshev center, think of it like it's the most middle point you can find within the polytope. It's a well-defined center. And this is useful for a few reasons. If you need just one point to represent the whole area of uncertainty, the Chebyshev center is a good choice. It can also be a starting point for algorithms that explore the polytope, like the sampling methods we'll talk about later. Now, that linear programming problem they give it tries to find a point x and a radius r so that a sphere centered at x with that radius r fits completely inside all the half spaces defined by x, a, b. And the goal is to make r as big as possible. That condition they have, the one that says ax plus a1 to 2ab, it makes sure the center x is at least a distance r away from each hyperplane. This distance has to do with the norm of that normal vector, written as ai. So in simpler terms, the Chebyshev center gives you a solid way to find a central point within your uncertainty zone.
Okay, I'm starting to see how all these pieces fit together, how the geometry and the probabilities start to connect. Now we get to the n-dimensional unit cube, which they call Qn. They define its A and B matrices using these identity matrices, vectors of ones and zeros. This seems like a very simple basic H polytope, like a building block maybe.
You got it. The unit cube, it's a fundamental example of an H polytope. The way they define A and B, it just sets the rules for a cube centered at the origin with sides of length 2, that's from -1 to 1 in each of those n dimensions. And using identity matrices makes the A matrix very sparse, meaning it's mostly zeros. This sparsity is super important for efficiency. It means the storage cost only grows linearly with a number of dimensions n. That's a good thing, especially when you're working in high-dimensional spaces. So the unit cube, it's like a simple, easy-to-understand shape we can use to build more complex things.
I like it. Start simple, build up from there. Makes sense to me. Then they explain how you can take that unit cube and change it to have a specific mean. They call it marrying stereo. And a covariance matrix, a barico. They call this new polytope Q. They use a formula involving the matrix square root of y. It's like they're creating a more general kind of uniform distribution centered where we want it.
Yeah.
And with the shape of uncertainty we need.
Precisely. This transformation to Q, it lets you create a uniform distribution over a parallel pipette. It's like a skewed, stretched out cube centered at the mean. And its shape and orientation are all controlled by that covariance matrix. The matrix square root, phi, is what makes that shaping happen. Now that factor of 12, that comes from a uniform distribution on the standard interval matic 12, which has a variance of 112. Think of it like this. After a little shift, our initial unit cube basically matches this interval in each dimension. So we need this factor to make sure that QQQ ends up with a desired covariance in simpler terms. In simpler terms, it's a way to represent a more general kind of uniform uncertainty, one that matches the statistical properties we need.
Okay, so it's like taking that simple cube and stretching it, twisting it, to fit the specific uncertainty we have, right? Now, they give the standard way to define that matrix square root, tref, using the eigendecomposition of Quayle. That's a pretty common technique in linear algebra.
Oh, absolutely. It's a classic. The eigendecomposition error is aved AFAT. What it does is break down the covariance matrix into its principal components. Those are the eigenvectors in V. And the eigenvalues are on the diagonal of that matrix. Those represent the variances. To get the square root, you just take the square root of each eigenvalue and reconstruct the matrix so you get VVTT. What this does is stretch and rotate the unit cube along those principal directions, by amounts proportional to the square roots of those variances. And that's how we get the desired covariance structure for our uniform distribution.
It's pretty neat how they take these techniques from linear algebra and apply them to this geometric representation of uncertainty. Then they talk about the storage cost of Q(on). They point out it can still be OAN if we can find a sparse square root decomposition of a matrix. Again, efficiency being important, especially as we go to more dimensions.
That's exactly right. If that covariance matrix 2 has a structure that allows for a sparse representation of its square root, then the storage needs for Q stay manageable. They grow linearly with the number of dimensions. That's a big plus when dealing with complex systems, the ones with lots of variables interacting with each other.
Right, because the more variables you have, the more important it becomes to keep things computationally efficient. Makes sense. Okay, the last bit in this section on polytopes, they remind us how a point C on a hyperplane and a vector V that's normal to it, perpendicular together, define the hyperplane in the familiar form X, E, B. It's like a geometry refresher.
It is. That normal vector V, which corresponds to the row vector A in our inequality, It sets the direction of that flat surface. And the point C, well, that anchors it in space. The equation Vanc x is b, or x equals b, that defines the hyperplane itself. And the inequality Vxx, or xa, that defines the half space on one side of it. It's a very fundamental way to describe these boundary surfaces.
But it all comes back to those basic geometric concepts, doesn't it?
Okay,
So we've laid a good foundation with all this talk about convex polytopes. Now let's get into Bayesian inference itself, the big picture. They start by talking about prior information, which they call X, and any related external information, T. Both are described by probability distributions. This is our starting point, what we believe initially, right?
absolutely. In Bayesian inference, you always start with what you already think about the thing you're trying to understand. That's XX, the prior. This belief is shaped by any previous knowledge, assumptions, past data, all that's summarized in T. And it's all expressed as a probability distribution. That's what quantifies your uncertainty, how sure you are.
Okay, so it's all about starting with what we know and how confident we are in that knowledge. Then comes the new information, the measurement. They call it Y. And it also comes with its own uncertainty, also a probability distribution. This is the data that helps us refine our initial belief, right?
Exactly. Y gives you new evidence about X, but measurements are never perfect, There's always some error, some uncertainty. That's why we describe it with a probability distribution, too. It tells us how likely different measurement outcomes are.
Got it. Measurements aren't perfect. We have to factor that in. Now, they present the core formula of Bayesian inference, Bayes' theorem in all its glory. It's written as PXR, PXR, PYT, PXR, PXR. Can we break this down piece by piece? What do all these terms actually mean and how do they work together?
Of course. So PXRT, or PXRYT, that's what we call the posterior distribution. This is the end goal, what we're after. It's our updated belief about X after we've seen that new measurement, while given all the prior info, T. Then there's PYXR, the likelihood. This tells us how likely it is to see the measurement Y if the true value of X was a particular value. Taking into account everything we know in T, PXRT, is our prior, what we believed about X before we even saw the data, again, giving T. And finally, PYT is the marginal likelihood, sometimes called the evidence. It's the overall probability of seeing the measurement Y based on our prior beliefs, T. It's like a normalizing constant to ensure that the posterior integrates to 1. So for you, what Bayes' theorem does is it gives you the mathematical recipe for updating what you believe in a logical, rational way using new evidence.
Okay, that was a great explanation. It makes a lot more sense now when I see how all the pieces fit together. The paper mentions that all the methods they're going to talk about are ways to approximate this Bayesian inference. Why is that?
That's a really important point. For complex systems, lots of variables, intricate relationships, or when you have tons of data trying to calculate that exact posterior distribution, well, it becomes practically impossible. The math gets too intense. That's why we need these efficient and reliable approximation techniques. And what this paper does is it explores a whole family of methods using this idea of convex polytopes to get those approximations.
Right. So we're looking for clever workarounds because the perfect solution is often out of reach.
Yeah.
Very cool. All right, let's get into the first method they present, the convex polytope filter, or CPF. They're basically reformulating those classic linear filtering methods, but using these uniform probability distributions over H polytopes. That's a really interesting twist.
It's a very fresh perspective. They begin with a standard linear state estimation problem. Let's say we want to track the state of some system. We represent the state with a vector, xk, at a specific time step, hk. Then we get a measurement, yk, and it's linearly related to that state yk equals hkxk plus eq. Hk is a matrix that describes how the measurement relates to the state, and eq is the noise, the uncertainty in our measurement.
So they're starting with a very basic model, a linear system. But then the key assumption in this CPF framework is that measurement noise, it's not just random, it's specifically uniformly distributed over some H polytope peak. That seems like a really specific choice for the noise.
It is specific, yes, and that's what lets them use the geometry of polytopes for you. Since that noise, HK, is uniform over peak, and because the measurement model is linear, that YK is also uniformly distributed, but over a different H polytope, PYK.
So the uncertainty changes shape, but it's still a uniform distribution over a polytope. Interesting. And they say this new polytope, PYK, it's just a fine transformation of the original noise polytope, PY. It's written as PYK plus HKXK. That makes sense, that linear measurement operator HK, it just takes the noise shape and shifts it around based on the current state, XK.
That's exactly right.
Yeah.
And then they make another assumption. That our prior uncertainty about the state that's xk, our belief about xk before we get the measurement at time xk, is also uniformly distributed, but this time over its own h polytope, pxk. So now we've got both our initial guess and the uncertainty in our measurement represented geometrically as uniform distributions over polytopes.
Okay, so we've got polytopes for our prior belief and for the measurement uncertainty. What do they do next?
This is where it gets really cool. They take that measurement polytope, pyk, which is in the measurement space where ak lives, and they transform it back into the full state space where x is. This gives them a measurement h polyhedron, phyk equals h pyk. Now that hk looks like a pseudo-invert of hk. What's that all about, and why does it become a polyhedron instead of staying a polytope?
Yeah, that's a good question. What's going on there?
It's a really insightful question. See, the matrix HK, what it does is it maps from the state space where XK is to the measurement space where YK is. To go back from the measurement to our understanding of the state, we need something like an inverse. But here's the thing, in many real-world situations, our measurements don't capture everything about the state. For example, imagine our state has 3 variables, like a position in 3D space, but our measurement only gives us 2 pieces of information, like a 2D image. In that case, HK can't be inverted in the usual way. That's where the pseudo-inverse comes in, written as HK. It gives us a way to go back from the measurement space to the state space, but it can create a shape that's unbounded in some directions, even if PYK was bounded in the measurement space.
Okay.
Think about that 3D position example. A 2D image might tell us a lot about 2 of the position coordinates, but the third one could be anything, we don't know. That unboundedness is why PHYK becomes a polyhedron. It might not have those nice finite boundaries anymore, but importantly, you don't actually have to calculate this pseudo-inverse directly, which is great for computation.
I see. So it's like the measurement doesn't give us the full picture. And that can make things a bit messy, right? But we can still work with it. Now, what's the main idea behind this convex polytope filter?
The heart of the CPF is this. The posterior distribution for the state, pxx, it's uniform over the intersection of our prior h polytope, pxr, and this measurement h polyhedron, phyk. Basically, the updated region of possibilities is just where what we initially believed overlaps with what the measurement tells us.
So we're finding the common ground, the agreement between our prior belief and the new data.
Exactly. And because the intersection of an h polytope and an h polyhedron gives you another h polytope, assuming the intersection is bounded, which it would be if the measurement gives us some useful information, we have a really elegant way to update our belief about the state. They do mention that a similar concept has been explored before, but they emphasize that their derivation is independent. So with the CPF, you're updating your uncertainty by finding that geometric overlap between what you thought before and the constraints imposed by the measurement.
It's like a puzzle, agreeing on where those pieces fit together. Okay, in remark 3.1, they talk about how the CPF handles propagating the state through time. If the state evolves linearly, they write it as x up equals mkx up clearly plus sync, where mk is a linear model and sync is the model error, uniform on pick. They show that the propagated distribution for the prior at the next time step, pxuck, is also uniform on the new polytope, pxuck equals mkpxuck pick. This involves that Minkowski sum we talked about. But then they just say that computing this is generally impractical in high dimensions because of the difficulty of that sum. If it's so impractical, why even bring it up?
That's a fair point. You see, while directly using the Minkowski sum is hard, this remark is important because it shows us the conceptual underpinning of how the CPF ideally handles how uncertainty changes over time, even if it's not always doable in practice. It shows that even when things evolve linearly and there's uniform error in our model, our belief stays within this realm of uniform distributions over polytopes. But the fact that the Minkowski sum is such a pain in high dimensions, that's why we need approximations and ensemble methods later on in the paper. It's more of a theoretical stepping stone to show the underlying structure of uncertainty propagation, even if we can't always calculate it precisely. So it tells us how uncertainty grows and changes shape over time in principle, even if we need more practical ways to actually do it.
I see. So it's good to know the ideal scenario, even if it's not always achievable. Okay. Now we're on to the extended convex polytope filter, or ECPF. This is designed for when our measurements are nonlinear, not those nice linear functions we've been assuming. They write it as ik equals hxk plus each xk, where h is some nonlinear function. They point out that even if the noise, each, is uniform, the true posterior usually won't be uniform over an h polytope if the measurement function h is nonlinear. That makes sense. Nonlinearities can really mess with the shapes of distributions.
That's exactly it. When you apply a nonlinear transformation to a uniformly distributed polytope, which is our prior belief what comes out in the measurement space, and then what you infer back in the state space, it usually ends up with a much more complex shape that's not uniform over a simple polytope anymore.
So what they're trying to do with the ECPF is to linearize that nonlinear measurement function, h, so they can still approximate the posterior with an h polytope. That's where lemma 3.2 comes in. It gives us a first-order affine approximation of the right inverse of HKX. That sounds a lot like a Taylor series approximation.
You're right. It's a good analogy. Lemma 3.2 basically provides a local linear approximation of what would be the inverse function of that nonlinear h. It does it around the prior mean. What this does is let us approximately undo the nonlinear distortion in the measurement and bring that information back into the state space in a linear way, at least in a small neighborhood around the mean. Now, HK, that's the Jacobian matrix of the function evaluated at the prior mean. The Jacobian captures the local linear behavior of h around that specific point. So in essence, this lemma lets us pretend the measurement is kind of linear so we can continue to use polytopes.
I see. A clever trick to simplify things.
So
Welcome back for another deep dive.
always a pleasure to be back.
So today we're going to be looking at something that I find pretty fascinating.
Yeah.
And that is this whole idea of, like, we talk about Bayesian inference as this, ideal way to learn from data, right?
Right.
We update our beliefs. It's all mathematically sound.
Yeah.
But then you try and apply that to anything complex in the real world.
Yeah.
And it all falls apart because of computational limitations.
Yes. You hit the wall.
Yeah, you hit the wall.
Hard.
So we end up having to do all sorts of like approximations and compromises.
That's right.
And the paper we're looking at today is kind of taking a completely different approach to that problem.
Absolutely.
And this is, it's a paper that proposes this geometric approach to doing Bayesian inference.
Yeah.
Using these things called convex polytopes.
Yeah.
Which sounds kind of out there, right?
A little bit. A little bit.
But the potential payoff is huge, I think.
Oh, absolutely.
Like if this works, we could see like much better approximations in areas that are computationally really difficult.
Right.
Like predicting the weather or, keeping track of robots in some crazy environment.
Current state estimation, data assimilation problems.
Yes.
The really hard ones.
Right.
So this is a shortcut to being well-informed.
I like it. All right. So we've got this one research paper that we're diving into today.
Yes.
And the mission, I guess, is we want to unpack this whole geometric approach.
Okay.
I mean, really trying to understand, like, starting from the very basics, what are these convex polytopes?
All right.
How do they work? How can you use them to build these Bayesian filters?
Yep.
And then get into some of the more advanced stuff with, like, ensemble-based versions.
Okay. Sounds good.
We're going to get into the mathematical details.
All right.
So buckle up.
Let's do it.
All right. So the paper starts out by saying there's these two main ways to describe a convex polytope.
That's right.
You've got a V polytope, which is defined by like all of its corners, the vertices.
That's right.
So if you took like a bunch of points and you drew the smallest convex shape that enclosed all of them, that's a V polytope.
That's it. Okay.
Okay.
Yeah.
And then you've got the other way, an H polytope.
Right.
Which is defined by all of its like flat boundary surfaces, the hyperplanes.
Yes.
So like you've got this multidimensional space, you're cutting it with a bunch of planes.
Uh-huh.
And the region that's enclosed is the H polytope.
That's it.
Okay, so two ways to think about these shapes.
Yeah.
Now this paper chooses to focus on H polytopes exclusively.
Yeah.
And they say that it's because it's easier to add hyperplane constraints.
It is.
So in the context of Bayesian inference, why is that such a big deal?
So the idea is that in Bayesian inference, you have some some initial guess as to what the state of the system might be.
Yeah.
And then you're given some data, right?
Yeah.
Some measurement.
Yeah.
And that constrains the possibilities. And so if you're representing your uncertainty as an H polytope, so a set of linear inequalities,
Okay.
adding a new piece of information is just adding another inequality.
Oh, okay.
It's just another hyperplane constraint.
Okay.
So it's a very natural, computationally straightforward way to update your representation of uncertainty.
Okay.
If you used a V polytope, adding a new piece of information might mean you have to find new vertices
Right.
and redefine the entire convex hull, which is computationally
Yeah, that sounds hard.
It's very difficult.
Okay.
Yeah.
So H-polytopes have a real advantage there.
For that.
Yeah. Okay. So then they give us this formal definition of an H-polyhedron as
Okay.
P sub H of A, B equals, and then the set of all X such that X is less than or equal to B, where X is an element of Rn.
Right.
Now A is this P by N matrix.
Right.
And B is a P-dimensional vector.
Okay.
So can we break that down? Like for someone who doesn't necessarily live and breathe linear algebra.
What are A and B in terms of these planes?
So
Like, how do we visualize that?
yeah, so X is our state vector.
Right.
So it's a list of all the variables we care about.
Okay.
A has P rows and N columns.
Right.
And each row of A, so a sub I transpose, where the transpose is just turning a row into a column,
Okay.
is the normal vector to one of the bounding hyperplanes.
Okay.
And then B sub I is just telling you about the position of that hyperplane in space.
Okay.
So a sub I transpose X less than or equal to B sub I means that for any point X inside the H polyhedron,
Okay.
if you take the dot product of a sub I with X, it has to be less than or equal to B sub I.
Okay.
And that defines a half space.
Yeah.
So everything on one side of a hyperplane in the H polyhedron is the intersection of all of those half spaces.
Okay, so it's like all the points that satisfy all of those inequalities at the same time?
That's right, yeah.
Okay.
And so A and B are just defining the orientation and the position of all of those.
Flat walls that enclose your H polyhedron.
All right, I think I got it.
Yeah.
So then they say an H polytope is P of A, B equals the set of all X, such that X is less than or equal to B, where X is an element of Rn.
Okay.
And the only difference seems to be here that an H polytope is a bounded H polyhedron.
That's right. Yeah.
So why is that boundedness condition important in this whole context?
So an H polyhedron could extend infinitely in some directions.
Okay.
An H polytope is finite in all directions. And so when you're talking about probability distributions, being bounded is a nice property to have.
Okay.
Because you generally think of probabilities as being concentrated in a finite region.
So it makes sense that you'd want to have a bounded shape.
Right, exactly.
Okay.
Yeah.
And then they introduce these shorthand notations.
Right, which are just to make the equations a little easier to write.
Okay, so like P sub H with a square and P with the square is just an abbreviation.
Yeah, they're just abbreviations to make things cleaner.
Okay.
Yeah.
Makes sense. All right, so they point out some key properties of H polytopes
Yeah.
that are going to be important.
Yep.
The first one is at the intersection of two H polytopes,
Okay.
or an H polytope and an H polyhedron
Yeah.
is also an H polytope.
That's right.
And mathematically, that's P1 intersects P2 equals the set of all X, such that A1 stacked on top of A2 times X is less than or equal to B1 stacked on top of B2,
Okay.
which seems pretty intuitive, right?
Yeah, so if a point's in P1,
Right.
it has to satisfy the inequalities defined by A1 and B1.
Right.
If it's in P2, it has to satisfy the inequalities A2, B2.
Okay.
So if it's in the intersection, it has to satisfy both.
Yeah.
And that's what that stack notation is.
Okay.
Yeah.
So in terms of like Bayesian updating, why is that property so important?
So when you get a new piece of information, that often acts as a new constraint
Right.
on your state. So it's like you're intersecting your prior region of uncertainty with the region that's allowed by the measurement.
Right. It's like cutting it down.
Exactly.
Okay.
Yeah.
All right. So the next property
Okay.
is about these affine transformations. So if you take an H polytope P1
Yeah.
and you apply an affine transformation,
Right.
C times P1 plus D,
Okay.
where C is an invertible matrix,
Right.
you get another H polytope.
Yeah.
So specifically, you get P of A1C inverse, comma B1 plus A1C inverse D.
Okay.
And they say that if C is not invertible, then the result is an H polyhedron.
Right.
So what's the significance of that invertible versus non-invertible?
So when the matrix C is invertible, the transformation is 1-to-1.
Okay.
So it's like stretching, rotating, or shifting the H polytope,
Mm-hmm.
but without collapsing any dimensions. If it's non-invertible,
Yeah.
you can reduce the dimensionality of the space. So think about projecting a three-dimensional cube onto a two-dimensional plane. So you're going from something 3D to something 2D.
Right.
Even if the original polytope was bounded,
Yeah.
the resulting shape might not be bounded in all directions.
Okay.
So you get an H polyhedron.
Interesting.
Yeah.
Okay, and then the last property here is this Minkowski sum. So
Right.
that's P1 plus P2.
Okay.
And that's defined as the set of all x plus y, such that x is an element of P1 and y is an element of P2.
Right.
And that's like taking every point in P1 and adding it to every point in P2
That's right. Yeah.
to create this new shape.
Yeah.
They mentioned that this Minkowski sum of two H polytopes is another H polytope.
Yeah.
But computing the H polytope representation of that sum in higher dimensions becomes practically impossible.
That's right.
So why does this become so hard as the dimensionality increases?
So the problem is that the number of hyperplanes needed to define the Minkowski sum can grow very rapidly. So if you have P1 defined by P1 hyperplanes and P2 defined by P2 hyperplanes, the number of hyperplanes to describe their Minkowski sum can grow exponentially with dimension.
Okay.
So even finding all of the hyperplanes, all of the equations,
Right.
becomes really computationally intractable.
Okay.
And the problem is that when you think about a system evolving through time with some noise added, the resulting uncertainty is often a Minkowski sum.
Okay.
And so if you can't compute that efficiently, it's a problem.
You can't track it directly.
You can't, yeah. And that's one of the big motivations for looking at these approximate methods.
That makes sense. All right. So then they define this uniform probability density function on a polytope P.
Right.
Which is given by U of X, semicolon, P equals 1 over the volume of P for X in P.
Okay.
And 0 otherwise.
Yeah.
Where the volume of P is just the integral over the polytope.
Right.
So that's a pretty straightforward concept, right?
Yeah, it's a uniform distribution, so everything inside the polytope is equally likely.
Right.
Yeah.
Okay.
And then 1 over the volume is just so that it integrates to 1.
Right. The normalization constant.
Exactly.
Okay.
Yeah.
And then they define this Chebyshev center of an H polytope as the center of the largest sphere that can be contained inside of it.
That's right, yeah.
And they give this linear programming problem to find this center, X sub C, and the radius, R sub C.
Okay.
And that problem is to minimize negative R, subject to X, plus the vector of the norms of all the A's.
Right.
Transpose times R less than or equal to B.
Okay.
So let's unpack that a little bit. First of all, why are we minimizing negative R?
So you want to find the biggest sphere possible.
Right.
So you want to maximize the radius. But in a linear program, you can only minimize.
Okay.
So minimizing negative R is the same as maximizing R.
Got it.
Yeah.
And then what about that constraint?
Okay, so the idea is that for a sphere to be entirely inside the H polytope, the distance from the center to each hyperplane has to be greater than or equal to the radius.
Okay.
So if even one of the distances is less than R, then the sphere is poking outside.
Right. Okay.
And so the constraint is just saying that the distance from the center of the sphere, X, to each hyperplane has to be at least R.
Okay.
Yeah.
Okay, so it's a geometric constraint.
It is, yeah.
Expressed mathematically.
Exactly.
That's
Yep.
right. Then they define the n-dimensional unit cube, Q sub n, as this H polytope.
Right.
With a very specific A and B.
Yep.
So that's Q sub n equals P of the identity matrix stacked on top of the negative identity matrix, comma, a vector of 1 stacked on top of a vector of zeros.
Okay.
So walk me through this notation. Why does that describe a cube?
Okay, so the identity matrix I sub n is just a matrix with 1s on the diagonal and 0s everywhere else. And 1 sub n is a vector of all 1s, and 0 sub n is a vector of all 0s.
Okay.
And so when you do that stacked matrix multiplication, you end up with 2 sets of inequalities.
Right.
One saying that each component of x has to be less than or equal to 1.
Okay.
And one saying that each component of x has to be greater than or equal to 0, which is exactly the definition of the unit cube.
All right. So it's a clever way
it is,
represent it.
Yep.
Okay. And then they show how to modify that unit cube
Right.
to have a desired mean,
Yep.
mu, and a covariance sigma.
Okay.
And that gives us Q mu sigma equals
Right.
The square root of 12 times sigma to the 1/2 times the identity matrix times Q sub n minus 1/2 times a vector of 1s plus mu.
Right.
And they also state that the expected value of the uniform distribution on that transformed cube is mu.
Yep.
And the variance is sigma.
That's right.
So first of all, where does that square root of 12 come from?
Okay, so That factor comes from the variance of the uniform distribution on the unit interval.
Okay.
So if you have a random variable that's uniform on 0 to 1, its variance is 1/12.
Okay.
So the unit cube
Yeah.
can be thought of as n independent copies of that.
Right. In each dimension.
Yeah, exactly.
Right.
And so if you center it at the origin, the covariance matrix would be 1/12 times the identity,
Sure.
but you want it to have covariance sigma.
Right.
So you need to scale it by the square root of 12 to correct for that factor.
Okay. So it's a scaling factor.
It is.
Okay.
Yeah. Yeah.
And then adding ma is just shifting it to the right.
Great, translating it.
Exactly.
Okay. And then they mention that the matrix square root of sigma to the 1/2,
Yeah.
is typically computed using this eigendecomposition, sigma equals v lambda v transpose,
Right.
where lambda is this diagonal matrix of eigenvalues,
Mhm.
and v is the matrix of eigenvectors.
Right. So sigma to the 1/2 equals v times the square root of lambda.
Right.
And they say that there's this potential order n storage cost
Yep.
if a sparse decomposition is used.
Right. Yeah.
So in high dimensional problems, why is this sparsity thing so important?
So in high dimensional problems, the covariance matrix can be really big.
Okay.
It's n by n.
Uh-huh.
And storing that can take a lot of memory, order per n squared memory.
Right.
But a lot of real world systems have a kind of local or structured dependence.
Okay.
And so their covariance matrix is sparse.
Right. So a lot of the entries are 0.
Exactly.
Okay.
And so if you can represent the square root of sigma in a sparse way,
Uh-huh.
it can save you a lot of memory.
Oh, and it makes it actually possible to do these
It
computations.
does, yeah.
Okay.
Yeah.
All right. So the last thing they mention in this kind of background section
Okay.
is how a hyperplane is defined by a point C on it and a normal vector V.
Right.
And that gives you this algebraic representation. A equals V transpose. B equals A times C.
Yeah.
And the inequality X is less than or equal to B
Okay.
for all points X on the opposite side of the hyperplane
Right.
of the normal vector.
Yes. So this is just saying that you can represent the geometry of a plane
Uh-huh.
with equations.
Right. So it's linking that geometric idea with
Yeah,
the math.
exactly.
Okay.
Yeah.
So that's the end of our convex polytope background discussion.
Okay.
Now we can get into the convex polytope filter,
All right. Let's do it.
right, or a CPF.
Yep.
So they start this section out
Yeah.
by saying they're going to reformulate classical linear filtering in terms of uniform distributions on H polytopes.
That's right. Yeah.
So we've got this linear measurement model.
Okay.
Y sub k equals H sub k x sub k plus eta sub k.
Right.
So Y sub k is our measurement at time k.
Yep.
X sub k is the true state.
Mhm.
H sub k is our measurement operator. And eta sub k is the measurement noise.
Okay.
And they specifically assume that the measurement noise eta sub k is uniformly distributed
Right.
on an H polytope.
It is. Yeah.
P sub eta sub k.
Okay.
So that's a key geometric assumption.
It is. Yeah.
Wow.
So if you assume that eta sub k is uniform on p sub eta sub k,
Yeah.
then the uncertainty in your measurement, y sub k, is also uniform on a related H polytope,
Okay.
p sub y sub k.
So what's the connection between those two H polytopes?
So p sub y sub k is just an affine transformation
Right.
of p sub eta sub k.
So it's the same shape,
Yeah.
just shifted.
It's just shifted.
Yeah.
Exactly. Yeah.
So then we've got this prior belief about the state x sub k,
Right.
which is also represented as a uniform distribution on an H polytope,
It is. Yeah.
px minus sub k.
Okay.
So
Oh.
how do we combine that prior uncertainty
Uh-huh.
with the uncertainty we have about the measurement?
So you can use that property we talked about earlier,
Right.
the intersection of H polytopes being another H polytope.
Oh.
So the measurement y sub k gives you information about H sub k, x sub k plus eta sub k.
Right.
And since, the distribution of eta sub k,
Yeah.
you can think about what range of H sub k, x sub k could have led to your measurement.
Okay.
And then you use what's called the pseudo-inverse of the measurement operator H sub k
Uh-huh.
to bring that uncertainty back into the X space.
Okay.
And so you get this measurement H polyhedron,
Right.
P sub HY sub K in the full state space.
So it's kind of like...
So that represents all the possible values of X sub K
Yeah.
that are consistent with your measurement,
Okay.
given the noise.
Right. So we've got this region in the state space that could have produced our measurement.
Yeah.
And our prior belief about the state is also an H polytope.
It is, yeah.
So it seems natural to just kind of find the overlap
That's right.
between those two.
You take the intersection.
Yeah.
Yeah.
And because of that intersection property, we know that the posterior is also an H polytope.
That's right, yeah.
So the posterior for x sub k, after seeing the measurement, is just a uniform distribution on that intersection.
Exactly.
Okay.
Yep.
So that's the core idea of the CPF.
That's it.
All right.
Yep.
They then talk about like propagating that uncertainty forward in time.
Okay.
And they say that if the state evolves linearly, according to x minus sub k equals m sub k times x plus k minus 1 plus x sub k.
Right.
Where m sub k is like a state transition matrix.
Yeah.
And x sub k is process noise, which they also assume is uniform on an H polytope.
Right.
Then the predicted distribution at the next time step would be the Minkowski sum.
It would, yeah.
But they point out that that's computationally intractable in high dimensions.
You can't compute it.
Right, we talked about that.
Exactly.
So that's a big limitation.
It is, yeah.
Okay, so the CPF works when we have linear measurements and we assume uniform noise.
That's right.
But in the real world, we often have nonlinear measurement.
We do. So
That brings us to the extended convex polytope filter, or ECPF.
okay.
So when the measurement is nonlinear,
Right.
let's say y sub k equals h of x sub k plus eta sub k,
Okay.
even if the measurement noise is uniform,
Yeah.
the posterior is not necessarily uniform on an H polytope anymore.
That's right, because you've distorted things.
Right, because that h of x sub k is messing things up.
It is, yeah.
So the goal of the extended CPF is to get around that
Right.
by approximating the nonlinear measurement with a linear one.
That's right.
So they introduced this lemma 3.2,
Okay.
which gives us a first order of approximation of the inverse of the nonlinear measurement.
Right.
So h inverse sub k of z is approximately equal to mu minus sub k minus h inverse k of mu minus sub k
Right.
times h sub k of mu minus sub k
Okay.
plus h inverse of mu minus sub k times z,
Right.
where mu minus sub k is the mean of the prior,
Yep.
and h sub k of mu minus sub k is the Jacobian of h sub k evaluated at the prior mean.
That's right.
So why are we approximating the inverse of h?
So the idea is that your measurement, y sub k,
Yeah.
is related to h of x sub k.
Right.
And you want to infer something about x sub k.
Yeah.
And so if you had the inverse function, you could just directly apply that to y sub k
Right.
and get x sub k.
Okay.
So the problem is that the inverse might not exist,
Yeah.
or it might be too complicated to work with.
Right.
So by linearizing h around the prior mean,
Yeah.
you get an approximate linear relationship
Okay.
between z in the measurement space and x in the state space.
All right. So that lemma is giving us an estimate of what state x would produce a measurement z.
That's right. Yeah.
Okay.
Yep.
And then using that linearization, theorem 3.3 gives us an approximation of the measurement h polyhedron in the full state space.
It does. Yeah.
So p sub hy sub k is approximately equal to h sub k of mu minus k pseudo inverse times p sub y sub k plus mu minus sub k minus hk of mu minus sub k pseudo inverse times h of mu minus sub k.
Right.
So
let's break down that formula.
Sure.
What do the different parts do?
So p sub y sub k is your measurement uncertainty, and you're pre-multiplying it by that pseudo-inverse of the Jacobian to transform it into the x space.
Okay.
But then you have to shift it to account for the fact that you linearized around the prior mean.
Right. Okay.
Yeah, and so the other two terms are just doing that.
Okay, so it's taking the measurement uncertainty and putting it back into the state space.
It is, yeah.
In an approximate way.
That's right.
Okay. And then, just like in the original CPF,
Yeah.
the posterior in the ECPF is approximated as the uniform distribution
Right.
on the intersection of the prior H polytope
Yep.
and that approximate measurement polyhedron.
Exactly.
Okay, so it's essentially forcing the nonlinear problem
That's forcing it.
into a linear framework.
That's right.
Okay.
So they give some examples of the CPF
Yeah.
and the ECPF in Figure 1.
Okay.
The CPF example,
Yeah.
the prior is a square,
Right.
which is a 2D polytope.
Yep.
And they have this linear measurement of just the first component of the state
Uh-huh.
with some uniform noise
Okay.
and the posterior H polytope.